Good morning. My name is Neil. I'm a software engineer on the Hermes team at Meta. Hermes was actually announced right here at Chain React 5 years ago in 2019. And I think we have a couple more users since that time. Could I see by rough show of hands how many of you are currently using Hermes? Oh, wow, OK. And how many of you have heard about Static Hermes or watched Svetan's talk last year? OK, and don't worry if you haven't. We'll cover everything that you need to know for this talk. So today I want to tell you about how Static Hermes really improves the performance of existing Flow and TypeScript code. Since we announced it, some of you in the community have been brave enough to even try checking it out and experiencing this firsthand. So before I do that, though, I'm going to take my life in my hands for a moment and try to show you something live. So one of the benchmarks that we've been using to measure Static Hermes performance is a ray tracer from Microsoft's TypeScript samples repo. We really like this benchmark, and we thought it would be perfect for this talk because I have it on good authority that no React Native app is complete without a JavaScript ray tracer. So we downloaded the ray tracer, removed all of the types, and wired it up to some UI, and ran it through Hermes in interpreted mode. Let's load that. So here we're going to build it and run it. And so here we have some state-of-the-art graphics from the 1990s. But the ray tracer is actually doing a lot of work here. On each frame, it has to simulate how light interacts with each of these objects in the scene and generate those detailed reflections and shadows that you can see. So let's see what happens. Oh. Let's swap this. So instead, now we're calling the typed version. So here we can see we're calling the sad, slow, untyped version. Let's see if we switch it to use types that Static Hermes can use to improve performance. And all right. So we can see that the untyped version is chugging along at a respectable 1,200 milliseconds. This is a computationally intensive workload. And let's try running the typed version now that we've switched to that. So immediately, you can see that this is much faster. Let me show them side by side. So on the right, you have the untyped version. And on the left, you have the typed version. And we're printing the render times behind. And you can see that the untyped version takes around 1,200 milliseconds to 1,300 milliseconds to render each frame. The typed version does it around 10 times faster in around 120 milliseconds. So through my talk, I want to walk you through how Static Hermes does this. How does it take advantage of type information to optimize this code down to running 10 times faster? So with that, let's go back to the safety of the slides. All right. All right, so before I talk about optimizations, I wanted to briefly introduce you to what Static Hermes is. Static Hermes is the code name for the next generation of Hermes, which is the default JavaScript engine for React Native apps. The Static Hermes compiler can take advantage of optional sound type annotations in your code in order to improve performance. Like Hermes, Static Hermes can produce compact bytecode, but it can also produce fast native binaries like the ones we just saw. These native binaries can also tightly integrate with existing C code. So you can call directly from Static Hermes into native libraries and get tight native integration. So this has a lot of benefits. For one, it allows us to incrementally improve the performance of existing code with modest changes. Our goal is to combine the usability and safety of JavaScript with the performance and native interop of a language like C++. So all of this is to say that you wouldn't have to switch to C++ when you want the maximum possible performance or you want to call into a native library. So Static Hermes has been developed fully in the open on the Static H branch of the Facebook Hermes repo. And while it's not quite ready for general use yet, we've implemented a number of important typed optimizations, a number of important typed features, like unions, classes, and generics already. And as you've seen, we've had pretty promising performance results. We've also been working on JavaScript spec compliance for untyped code and making improvements to the performance of untyped code. And we're hoping to make these improvements available incrementally before all of the typed work is ready. So let's recap where the performance of the benchmark was. We started out at 1300 milliseconds for the untyped version of the benchmark, and we brought it down to 120 milliseconds by adding types. So over the rest of the talk, I want to show you how Static Hermes accomplishes this dramatic 10x speedup. So to understand how these optimizations work, we first need to understand how the Hermes compiler works. So this is a simplified pipeline diagram of the Hermes compiler. It operates in a few important stages. The first stage is the parser, which takes in JavaScript source and processes it. The result of that is fed to the type checker, which analyzes the user-provided type annotations and infers additional types. It also checks that those types are correct. The result of that is then fed to the optimizer, which runs a series of optimization passes to make the code more efficient. And finally, that goes to either Hermes bytecode or to produce a native binary. For this talk, we're mostly focused on the type checker and the optimizer, because that's really where this speedup occurs. First, we're going to talk about the type checker. So the key difference between Static Hermes and existing JavaScript type systems is that Static Hermes requires the types to be sound. This means that the type of a value that's annotated in the source has to match its actual runtime type. This is the secret sauce that allows Static Hermes to optimize with types while remaining completely safe. Existing JavaScript type systems like Flow and TypeScript don't require this because the type information is erased before the code is run. This is not a deficiency in Flow or TypeScript. This is just a really hard problem. So in order to achieve this in Static Hermes, we have to modify some JavaScript semantics and add some additional compile time and runtime checks to enforce this soundness. It's important to note that this typed code, the soundly typed code, can coexist with your existing untyped code. So types can be adopted incrementally in your code in just the places where you need the maximum possible performance. Let's take a look at a concrete example to see how soundness and unsoundness works. So here we have a simple function addXy that takes two parameters, x and y, which are annotated to be numbers. It adds them together and returns the result, which is also a number. Below, we're calling addXy by indexing into this array A at indices 10 and 11. So we can immediately see that these accesses are out of bounds. So this means that because the array A only has 3 elements in it, both of these are going to be undefined. So existing JavaScript type systems would allow this, even though the annotated types on addXy of number would be violated at runtime. This is not a bug in TypeScript or Flow. This is just a really hard problem to do in a language that's as dynamic as JavaScript. In Static Hermes, the out-of-bounds access would be caught immediately, and it would throw a range error because you've indexed into this array past the number of elements that it has. This allows Static Hermes to make really strong guarantees about the types of x and y in the addXy function. And we can use those guarantees to make further optimizations. So let's take a look at the vector class from the benchmark for an example of how exactly this improves performance. Here's how it looks in untyped code. We have a class vector. It has 3 fields, x, y, and z. The constructor takes them in and populates them onto this object. This is what it looks like in typed code. The fields have been declared up front, and they're annotated with their types. The constructor has also been annotated with types, and it just populates those fields. This should all be pretty familiar. Let's see what happens if we want to do a simple operation, like load the z property from some value myvec that we know is an instance of the vector. So first, let's see what that looks like in untyped code. The first thing you have to do is check that myvec is actually an object. In JavaScript, we have no idea what the type of this value is. So when you try to load the property, we first have to check that this is actually an object. As you all know, JavaScript objects are dictionaries, which means that lookups are pretty expensive. Hermes performs some pretty aggressive caching in the interpreter in order to avoid the overhead of doing dictionary lookups every time. But even with caching, there are several steps involved. First, we have to get the cache entry for the read. Then we compare the object with that cache entry. If it matches, then we can do a fast load from the object at the cached offset. But if that doesn't work, then we have to fall back to the full dictionary lookup, which can be hundreds of times slower. With typed code, this is almost comically shorter. The compiler knows ahead of time exactly where the z property is. It knows the layout of the object, and it knows that myvec is an instance of the vector. So it simply loads from the offset 2. This is just a single assembly instruction. So another place we've seen types make a big difference is with array accesses. Here's another very simple example. We have a function that takes an array and an index, indexes into the array, and returns the value at that index. On the left, we have an untyped version, and on the right, we've annotated the parameters to the function and the return type. Let's go through the steps for how reading something from the array would work. Again, we have to first check that myArray is actually an object. Then we have to check if I is index-like, which means that I is an integer and it fits within 32 bits. If it is, then we can go to a special path where we attempt to do an indexed load from the object. After that, we have to check if the value is available. This means we have to check whether we've gone out of bounds or if you've done something like delete a property on the array. And if any of these checks fail, we fall back to the full dictionary lookup. In typed code, we just check that I is an integer because we already know that it's a number and that it falls within the bounds. If it is, we load from the array at I. So let's look at an expression that combines these and see how these inefficiencies can add up. So here we have myvec.z plus myArray at I. In untyped code, we would first do the slow property load from myvec and myArray that I previously described. Then we have to check that what we've loaded are both numbers. If they are, then we can add them as numbers. But if they're not, we have to fall through to the general case, handling all of the other things that can come to the addition operator, like objects, strings, big ints, anything really. In typed code, we have the very fast loads from myArray and myvec, and then we simply add them. Because they've already been annotated as numbers, we know that the thing that we've loaded is a number in both cases. So this is much faster. And with optimizations like the ones I just described, we were able to improve the performance of the ray tracer by 3x, going from 1300 milliseconds to 350 milliseconds. So this is great, but it's not quite the 10x performance improvement that we saw earlier. And that's because there are two other optimizations that we found that were really important to improve its performance. For that, we're going to move to the next stage of the compiler, the optimizer. The optimizer implements a wide range of compiler optimizations to improve performance. But there are two in particular that I want to talk about today, because we found that these made the biggest difference to the performance of the ray tracer. The first optimization I want to talk about is inlining, which is one of the most important optimizations for any compiler. Some of you may already know what inlining is, but for those of you who aren't, inlining is a pretty conceptually simple optimization. It looks at call sites, and where it can analyze the function that's being called at a particular point, it takes the body of that function and inserts it to the point where it's called. So instead of doing a call to the function, you just execute the code that that function would have otherwise executed. There are many reasons to inline. Code tends to have lots and lots of small functions, and we need these small functions. They help us build up all of the abstractions that we need to build great React Native apps. But these add up to significant overhead. If you're calling a very small function, the overhead of the call is larger relative to the amount of code that you're executing in the function. And most optimizations can't operate across calls. That's because most optimizations only analyze the code within a single function. So once they encounter a call, they can't see what's happening in the function that's being called. And because of that, this reduces opportunities for optimization. After inlining, all of the code is in the same function. So optimizations can see all of the code that was previously being executed and optimize across the two functions. So let's take a look at a concrete example. This is another example from the benchmark. we've extracted the sphere.normal method, which calls two functions, vector norm and vector minus, and we've got them here. So these are relatively small functions and are good candidates for inlining. They also call the new vector constructor. The first thing the compiler has to do is realize that the calls to vector norm and vector minus in the normal method are actually these two other functions that have been declared in the source. Once it does that, it realizes that these are good candidates for inlining and can inline the functions. So let's see what happens after that's done. So the calls to vector minus and vector norm here have been replaced with their contents. We can see in the first section of the code where we previously called vector minus, we've got the contents of vector minus there instead, and the result is being assigned to some local variable v. And where we previously had a call to vector norm, we're just taking the result of the previous call to vector minus and using that as the parameter. Within the compiler, these optimizations typically happen on Hermes' internal intermediate representation. But we're just showing you a source-to-source transformation here for simplicity. And there are still some calls here, right? There are still the calls to the vector constructors that I mentioned earlier. So the compiler can then identify that these are good candidates for inlining and perform a further round of inlining. So we eliminate the calls to the constructors and construct the final object directly in the normal method. The object creation here is represented as object literals, but these aren't actually object literals. These are actually typed class instances. Let's take a look at, all right. So the key to making inlining possible is that the compiler can determine which function is being called at any particular point. This is important because you need to know what you're calling in order to get its contents and put them in the place of the call. So here we have a very simple example. We have a function foo, which has a local variable op that's being assigned to some function. And then that value is being captured by the function bar, which calls op. In this case, the compiler is able to determine that op is only ever assigned to that single function. So inlining is possible here because the compiler can identify the target of the call to op. But it's very easy to break this. Let's modify the example slightly. So now op is assigned to one of two functions, depending on the result of a call to math.random. Now, the compiler doesn't know which of these two functions is being called. So the compiler can no longer perform inlining. We've managed to bamboozle the compiler. And so this has some interesting implications. Let's consider inlining methods, for instance. Here we have a base class, which has a single method, getID. GetID, it returns a number. And we have a derived class that extends base and overrides getID to return 42 instead. Below, we have a function called getID+1, which is very simple. It takes an instance of base and calls getID on it. Notice that the compiler here doesn't know which subclass of base you may have passed in here. It could be an instance of base. It could also be an instance of derived. Because of that, the compiler doesn't know what function is being called when you call base.getID. So this means that inlining isn't possible in this case. But that doesn't mean that all hope is lost when you try to inline methods. We can modify this slightly. So instead of taking an instance of base, getID+1 takes an instance of derived. The Static Hermes compiler performs an analysis across your bundle to see if a method is ever overridden anywhere in the bundle. If the method is not overridden, then Static Hermes knows that the getID+1 function is receiving an instance of derived, whose getID method is never overridden. In that case, it can annotate the call to getID with the actual getID function on derived, and inlining is possible here. After inlining, it can further optimize it. So now this is just returning a constant 43. So what used to be a property lookup and addition and a call is now just a static constant. So note that type information is really important to make this work. Here we've erased all of the types in the code. And we no longer know what derived is. Because of this, and because JavaScript is so dynamic, the compiler is no longer able to perform any kind of inlining here. So types really provide the information that makes this possible. I know that was a lot, so let me quickly try to recap what's really important to take away from this. Inlining is an optimization that eliminates calls by copying the function's contents. It really heavily depends on the compiler's ability to statically identify which function is being called at a particular call site. Inlining also unlocks many other optimizations, as we've just seen. So let's check back on what inlining does for our benchmark. We went from 1300 to 350 with types, and from 350, inlining brings us down to 210 milliseconds. But this doesn't get us to quite what we saw at the start of 120 milliseconds. And for that, we're going to go to the last part of the talk. So the last optimization I want to talk about is something called object elision. Object elision is also a conceptually simple optimization that helps break down abstractions in your code. It identifies objects that are only being used within a certain function and turns them into a sequence of local variables instead. So each field in the object is just turned into a local variable within the function where that object previously was. There are many reasons we want to do this. JavaScript tends to create many small objects, and while we've done a lot of work to make these allocations fast in Hermes, not allocating an object is still faster than allocating an object. So this makes object elision a really, really important optimization, especially after inlining. Analyzing values of the object fields is also really difficult. Like with inlining, the compiler typically can't analyze what's going on when a value is written or read from an object field, whereas it can if you're just reading or writing from a local variable. So let's pick back up on the inlining example and see what object elision would do to the code after inlining. Here we have the sphere.normal method again, where the constructors have been inlined and the typed objects are being created directly in place. The first thing object elision will do is identify that this variable v and the object that's being assigned to it is only used within the current function. Note that this isn't true for the object that's being returned from the function, because that object really does need to exist. It escapes from the function, and other things need access to it. So it then transforms each of the properties on v into local variables. So we can see that what used to be properties x, y, and z are now local variables vx, vy, and vz. And all of the accesses to them are now just reading from those variables. So this has eliminated both the object allocation and the property loads from the object. This kind of transformation also enables other optimizations. So let's take a look at how inlining and elision can interact in this relatively simple example. Here we have a class foo that has a single member bar. Bar is a function that returns a number. The constructor takes in an instance of bar and assigns it to the bar property. On the right, we have a function that creates an instance of foo, loads the bar property, and calls it. First, inlining can identify that the call to the foo constructor is a really good candidate for inlining. So we'll inline it, and now the object is being created directly in myfun. Then, object elision can identify that the object f is only being used within the myfun function. So object elision kicks in and eliminates the object. Now, what used to be a property on the object is just the local variable fbar. Finally, inlining can now see that fbar is just the function that we have above and eliminate the call. So we end up just directly returning 42. The key thing to take away from this is that each optimization will feed into other optimizations, and those optimizations will feed back into the first optimization. So in order to make your code as efficient as possible, Hermes will run each optimization many, many times. And with elision, we finally get to the 120 milliseconds that we saw at the start. Hopefully this has given you some sense for how the type information and aggressive optimizations in Hermes achieve this 10x speed up. Before we end, I wanted to give you a quick recap of what we've covered. Static Hermes enforces the soundness of declared types, and because it enforces their soundness, it's able to use the type information to speed up basic operations like property loads and array reads. Types also unlock additional ahead-of-time optimizations like inlining and object elision that wouldn't otherwise have been possible because JavaScript is so dynamic. These together dramatically improve the performance of typed code, as we've seen. And with that, thank you very much. If you have any questions, thank you. If you have any questions, please feel free to reach out to us after the talk. We'll be around. Reach out to us on GitHub by opening a discussion. If you want an introduction to Static Hermes, or you want to learn more about the native interop, you can watch Svetan's talk at React Native EU last year. And if you're interested in getting your hands dirty with the ray tracer benchmark, that's available in our GitHub repo.